Hello everyone, welcome back to Grade Up. My name is Deepti Mittal. So guys, in this video lecture, we are studying computer organization. Till now, we have completed two topics, basic organization in CO and second thing was machine instruction and addressing modes. We have taken overview of almost all types of instructions, data transfer, data manipulation, transfer of control, and we have covered all the addressing modes in detail. So guys, in this particular video lecture, we are going to start the new topic in CO, that is ALU, Data Path and Control Unit. Till now, we have studied the functioning of instruction or the basic things, instructions and these addressing modes and so many things. We have studied about instructions. Now we are going to study the concept behind CPU, how CPU actually processes our information. For this, we are going to study ALU, Arithmetic Logical Unit, data path, how actually data transfer is carried out within the CPU and control unit. So let us start with that. So first thing which we are going to study is PSW, which is Program Status Word. You will ask me, what is this PSW? Let us start with that. Guys, I told you whatever result or whatever computation is carried out by arithmetical logical unit, all the result is stored in my accumulator. Okay. One more thing we have observed while using so many instructions that there were so many things like flags. I was using sometimes 0, carry bit, sign bit, and I was using these type of things. So these information should also be stored somewhere. For this purpose, we use program status word. Whatever calculation is done by ALU, it stores the result into program status word. Program status word, as name suggests, whatever your program is doing at this point, that status will be reflected by this word. And this word consists of two things: accumulator to hold the result and flag register. You know, we are going to use so many flags like carry bit, Z bit, 0 bit, sign bit, and these things we are using. So these all information get stored in my flag register. What is a flag register? First of all, what is a flag? Flag is a flip-flop which is used to store one bit of information. You have studied flip-flop in your digital logic. If you have not studied, please refer those video lectures. Okay. Flag is basically a flip-flop which is used to store one bit of information. Okay. Now flag register is the group of those flip-flops, as we have studied register in digital logic, where we form a 4-bit register by combining or cascading 4 flip-flops. Here also same procedure has been carried out. So flag register is the combination of some flip-flops which is used to store some bit of data. Then again, which is categorized into two parts: conditional flags and control flags. So this conditional flag is used to hold the conditional data, which is like carry data, sign data, 0 bit. All these information will be stored in my conditional flag. And this control flag stores the control flow information for program execution. What type of information it is going to store? Interrupt. Direction flag, which will tell in which direction you are going to perform your indexing operation, and so many things. In this video lecture, we are going to study this conditional flag because it is important for our syllabus. Let us see what is conditional flag in detail. According to 8086 microprocessor, there are 6 flags which are present in my flag register. 6 conditional flags are there which are present in my flag register, which were carry flag, parity flag, auxiliary carry flag, overflow, 0, sign. Some of them you know already, some of them I will explain you. I will explain you each of them, but for some of them you are having a idea. So these flags are set or reset on the basis of result produced by ALU. That is, whatever is the result is in our accumulator, the value of flag is set or reset on the basis of the result. Let us see how it is being implemented in your system. We focused. First of all, we will see carry flag. I have represented this carry flag with C. This carry flag is going to hold the extra bit which is produced when you are going to perform some addition or subtraction operation. You are aware of this information. Let us see, let us make a quick glance what actually this carry flag is doing. See, it will check for the condition, is there any extra bit out of MSB? When actually operation has been performed, is there any extra bit which is coming out of my MSB, most significant bit? If this condition is true, then carry bit is set, otherwise reset. You know the meaning of reset, that is putting it to 0. Let us see how it is doing. You have to perform addition of 7 and 3. You know, for representing 7, I can use 3 bits and the representation is 1, 1, 1. For representing 3, again 3 bits can be used, 0, 1, 1. Then you are going to perform addition over here. 1 and 1, 0, 1 carry is given. See, you will say that this carry is produced. Now set the carry bit. I said carry should be out of MSB from this bit. Then only I am going to produce the carry set, then only I am going to set the carry bit as 1. Here 3 ones, then output will be 1 and 1 carry also generated. 1 and 1, again 0 and 1 extra bit generated. So this is a bit which is getting out of my MSB. So here carry bit will be set. In this manner, carry flag is implemented in our system. Let us move towards next flag, which is parity flag. You might have heard about parity in your computer network subject. Let us see what parity means. It is going to check the condition of accumulator, whether accumulator contains even number of ones. If your accumulator contains even number of ones, then this parity flag is set, otherwise it is reset. Suppose the result at some instant in the accumulator is this. Okay, count the number of ones, 1, 2, 3, 4, 5. This time number of ones are 5. Is it even? No, it is not even. Then parity flag will be set to 0. It will be used for serial data communication. When you are going to do serial data communication, it will be used for detecting the errors. This flag is used for error detections. Okay, let us move towards next type of flag, which is sign flag. This sign flag is set to 1 when the MSB of your output is 1. When suppose you have given data, here MSB bit is this, and if this bit is 1, then your sign bit is set to 1. And when this sign flag is set to 1, this means that your data in the accumulator is negative. And whenever data in accumulator is negative, for getting the actual data, you are going to perform 2's complement of that data. Okay. This is the idea with sign flag. Sign flag is used to find out whether the data is positive or negative. Whenever sign bit is set, it means data is negative, otherwise data is positive. Let us move towards next type of flag, which is auxiliary carry flag. The flags which we discussed before, carry flag, sign flag, parity flag, you might have heard about all these things, but this auxiliary carry flag is new to you. So be focused while studying this. See, the condition which it is going to check is there any extra bit from lower nibble to higher nibble? You know what a nibble is? I have discussed this thing in my first video. Nibble is a pair of 4 bits. Okay, and the condition is there any extra bit from lower nibble to higher nibble? If this condition is true, then set the auxiliary carry flag, otherwise reset the auxiliary carry flag. Suppose your accumulator is of 8 bits in 8085 microprocessor C. You are performing some operation. 2 inputs are given to you. Something like that. When you are performing operation, suppose you were performing addition. 1, 1, 0, 1, 0, 0 again. This time here 1 is given as carry. So see, this lower nibble is giving an extra bit to my upper nibble. This is the condition for auxiliary carry. Here auxiliary carry will be set because lower nibble is producing one extra bit for upper nibble. So you will say why I am using this particular flag in the flag register. What is the use of this flag? This flag is used for performing the BCD arithmetic. BCD means binary coded decimal. When you represent your binary decimal number system with the help of BCD, you are going to represent 0 to 9 decimals with 4 bits. I have explained this thing in my digital logic video lectures. So see it over there. So see the example how we are going to use AC for performing our BCD arithmetic. Example is add two BCD numbers 26 and 27. First of all, I will represent this 26 into BCD and this 27 into BCD. So represent it along with me. 2 will be represented by using 4 bits 0, 0, 1, 0. 6 again will be represented by using 4 bits 0, 1, 1, 0. 27 again 0, 0, 1, 0 and 7 again 0, 1, 1, 1. Now the operation is add. Then we have to perform addition over here. See 0, 1, 1, 1, 1, 0 and a carry is produced. Triple ones will produce output as 1 and extra carry. 1 over here. 0, 0 again 0, 1, 1, 0 and a carry is produced. 1, 0. So your output is this. So if you are going to read this output, what it is? You have to read it along, read it in the form of BCD. This is 4 and this is D. But in your BCD, you are allowed to represent only 0 to 9 numbers. You are not allowed to represent your D. But your accumulator output is this time 4D. Is it correct? Is it correct output? No, it is not correct BCD output. What is the correct BCD output over here is C. 26 and 27 when added will produce output 53, which will be 53. So your correct output will be 53. But what you are getting? You are getting 4D. So see, what is the procedure this PSW is going to take when produce output? See, this 4D is stored in my accumulator and AC bit is here 0 because there is no extra carry bit produced from lower nibble to higher nibble. So this AC is 0. See the justification given by PSW. PSW consists of two things, accumulator and flag register. In flag register this time AC is equals to 0 but 4D. I am getting output as 4D. For BCD, your each and every nibble should be less than 9. Here your lower nibble is D which is not less than 9. Then it is not a correct BCD, and to convert it into correct BCD, what you are going to do? You will add 6 to it. This is the procedure 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0. See guys, I have already mentioned this thing that for conversion of your incorrect BCD data to correct BCD, you have to add 6 to your data item. You are going to add 6 over here. 1, 1, 0, 0. This time one carry will be given 1, 0, 1, 0. This is the output. Now read it along with BCD representation. It will be 53. So here we have converted the incorrect BCD representation to correct BCD representation. So what was the idea? If any of your nibble is having data greater than 9, then add 6 to that particular nibble. Okay, let us see one more example. Here you are going to perform addition of 28 and 29. Write it in the form of BCD 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1. Perform addition 1, 0, 0, 1, 1, 0. This time an extra bit is generated from lower nibble to higher nibble. So my AC flag is set. Here 1, 0, 1, 0. So your output is here 51 in BCD. But if you observe this 28 and 29 addition, output should be 57. So I am getting the wrong output in BCD. But how? See how PSW is going to deal with this problem. This time PSW is going to check this accumulator value. Lower nibble is 1 and upper nibble is 5. Both are less than 9, so no problem. But this time auxiliary carry is set to 1. This auxiliary carry when set to 1 represents that this data is 1 in lower nibble, but it is more than 1. This value is 1 here, but it should be more than 1 because an extra carry is generated. So addition of 6 will be carried out over here for converting it into the valid BCD. So it will become 57. In this manner, your PSW, program status word, and your accumulator is going to deal with BCD arithmetic. Let us see one more example. Addition of 88 and 99. You know what it will be? 187. Okay, let us write it in the form of BCD. 10000, 10000, 1001, 1001. When you are going to perform addition over here, see 0010, 1 extra bit is generated from lower nibble to higher nibble. That is why AC will be set to 1, 110, 1001. This time, 1 extra bit is also generated out from MSB. Then carry will also be set to 1. This time carry bit is also set to 1. Now read it in the form of BCD. It will be 1, 2 and 1. So you are getting output as 1, 2 and 1. But your correct output is 187. So see how PSW is going to deal with it again. Here lower nibble is 1, which is less than 9. So it is correct. But AC is generated. So addition of 6 should be carried out. 6 is added over here. Again see this higher nibble. This higher nibble is 2, which is less than 9. It is correct. But carry bit is generated. What this carry bit shows that data was actually greater than 2. So addition of 6 also carried out with the upper nibble. So finally what we got as output is 187. In this manner your PSW is going to deal with BCD arithmetic. So let us just recall the procedure what we are going to follow. First of all, we will perform simple addition. Then we will check if any nibble value is greater than 9, then addition of 6 is performed. If nibble value is less than 9 and AC is generated, then you will add 6 to the lower nibble. And if a carry is also generated, then addition of 6 will also be carried out with our upper nibble. This is the procedure to perform BCD arithmetic using auxiliary carry flag. Now I think that you are clear with the concept of using auxiliary carry flag. Let us move towards next flag, which is 0 flag. 0 flag, as the name suggests, it will be set to 1 when your accumulator contains 0. Suppose you perform some operation and the output is 0. Then your 0 flag will be set to 1. Otherwise it will be reset, that is 0. Suppose you perform 4 minus 4. Then your accumulator will going to have 0. This time 0 flag is set to 1. Means Z is equals to 1 if accumulator is equals to 0. Otherwise no. This will be used for making like conditional jumps, as I have explained the conditional jump example while studying transfer of control instruction. I use this 0 flag over there. I told you that just take the overview, I will explain it. This is the same flag which we used over there. Let us move towards next flag. This is overflow flag. Guys, this flag is really important for your syllabus and question has been asked on this particular flag so many times. So study it very carefully. What is the condition we are going to check for overflow flag? See, there is a carry into MSB and no carry out of MSB, or vice versa. What does it mean? See, in carry and out carry, suppose you are having two numbers A and B and you are going to perform addition of this. This is the MSB bit of A, this is LSB bit of A, MSB bit of B and LSB bit of B. What this overflow flag is going to check, if there is one carry to this MSB and no carry out of this MSB, or there is no carry to this MSB and one carry out of these MSB, then your overflow flag is set, otherwise it is reset. See over here, suppose this carry into MSB is known as in carry and carry out of MSB is out carry. When your in carry is 0, this condition, and your out carry is 1, then your overflow flag is set. When in carry is 1 or out carry is 0, then your overflow flag is set, otherwise reset. So what we can say, when we are going to set our overflow flag, when C in and C out, if any one of them is 1, if only one of them is 1, then you are going to set your overflow flag. So how we can represent this equation? C in XOR with C out. Carry in when XORed with carry out. Okay. Let us see why we are taking this condition. One more thing. I told you that we are going to take overflow when we are having carry into MSB and no carry out of MSB, or vice versa. You should ask me the question why we are taking this condition. Let us see why we are taking this condition to set my overflow flag. Guys, as name suggests, overflow flag will be used to represent the overflow condition of my accumulator register. What is the overflow condition? Overflow condition means that you want to store data of larger size which a register can hold. That is, data is of more size than my register can hold. This is the condition when I am going to set or reset my overflow flag. Let us see it with example. Don't you worry about this particular expression. I will explain you this later. See, I have to perform addition of 7 and 3. Suppose we are going to perform addition on my signed data, and you know the range of signed data for a n-bit register. For n-bit register, you can store minus 2 raised to the power n minus 1 to 2 raised to the power n minus 1 data. This is the range for n-bit register to store signed data. This 7, I have to store this 7. Then how many bit register I need? This 7, when it is a unsigned data, I can represent it using 3 bits. But for signed data, it will be represented by using 4 bits. So 7 will be 0, 111, plus 3. It is plus 3, so it will be 0, 0, 11. Okay. When you are going to perform addition, see how you are going to perform addition. 1, 1, 0, 1, 1, 1 carry with 1, 0 and 1. Your output is 1, 0, 1, 0. You may think it is giving me output as 10. But it is not 10, because see how your accumulator is going to, your PSW is going to deal with this data. See, this is your accumulator result. This is 1, 0, 1, 0. Here your MSB bit is set now. Then it will be taken as negative signed. Signed bit will be set to 1. And whenever signed bit is set to 1, the actual output is 2's complement of the data. Then it will perform 2's complement of this data. 0, 1, 0, 1 and 1 addition. Then it will be 0, 1, 1, 0. Then you will get output as 6. Is 6 the correct output? Tell me, is 6 the correct output? No, 6 is not the correct output. This was the problem which we were facing with signed data. For this purpose, we used overflow flag. Let us see how problem is resolved using overflow flag. See here. Here, one carry was generated into MSB. There was one in carry but no out carry. Then here overflow flag bit will be set to 1. And now see the new justification which is given by our PSW. What PSW is going to do? PSW will observe that our accumulator data is 1010 and overflow flag is set to 1. When overflow flag is set to 1, it will assume that data is exceeding the range our accumulator can store. Okay, so it will take 1 extra bit, 1, 1, 0, 1, 0. This is your output. Okay. So our PSW will take the accumulator data 1 0 1 0, and this time it knows that overflow flag is set to 1. That is, your data is in such a way that it exceeds the range which accumulator can hold. So how PSW is going to deal with such problem? This time it knows that overflow has occurred and it is the positive overflow. Okay, this is positive overflow because see, the data which we has taken was 0 0 with their MSB bits. That is, we have performed addition of two positive bits. Then only overflow is occurring. Then it will take here one extra bit, which is, this was overflow flag. Then how it is going to read the data? 1 0 1 0 is the accumulator data, and because of positive overflow it will take one more bit extra, and now this data will be read as 10. In this manner you are going to get your out. See, in this expression I have taken this condition x, y, z bar, where x is MSB of operand 1, y is MSB of operand 2 and z is MSB of result. See, in this case overflow occurred when this was 0, 0 and 1. See this case, x bar will be 1 this time, y bar will be 1 and z will be 1. That is, this condition represents the positive overflow. Guys, one more thing. You can understand this basic thing that overflow can only occur if you are going to add two positive numbers or two negative numbers. So there are only two cases for overflow. First is positive overflow and second is negative overflow. When two negative numbers are added or two positive numbers are added, then only you are going to get the overflow. So this condition represents the positive overflow, and it is going to represent you the negative overflow. How it is going to represent the negative overflow, we will see. Here I have performed addition of 7 and minus 3. These are the signed data. How 7 will be represented? 0 1 1 1, and minus 3 will be represented in the 2's complemented form. How? 0 0 1 1 is the actual representation of minus 3, and the 2's complemented representation will be 1 1 0 1. Then you are going to add these two bits. You know how to calculate the 2's complement of a number. If you have some doubt, please refer the video which I have discussed this thing in my digital logic video series. So refer that series. 1 1 0 0 0 0 1. This 1 is given as carry. So 0, again 1 1, this 1 0 and 1. Here see, there is 1 bit into carry and 1 bit carry out of MSB. That is, in carry is also 1 and out carry is also 1. Then your overflow flag is this time 0. Okay, and this bit will be discarded basically. So how PSW is going to give the result? It will read accumulator. Accumulator is 0 1 1 0 1 0 0, and it will check overflow flag is 0. Then it will give output as 0 1 0 0, which is 4, which is the correct result over here. Okay, let us see the case where we are going to add two negative numbers. Let us see how we are going to add. This minus 7 will be represented in 2's complemented form. 0 1 1 is the original form and 1 0 0 1 will be the 2's complemented form. 1 0 0 1 and 1 1 0 1 is the 2's complemented form for minus 3. Perform addition. 0 1 1 0 1. This time we are getting one carry out of MSB, but no carry into the MSB. So here overflow flag is again set, and how it is going to produce the result? See, what is the value of accumulator here is 0 1 1 0, and your overflow flag is also generated. And what we know that this overflow flag is negative overflow. Then it is going to take 1 bit extra, which is 1, because it is the negative overflow. Then how result will be given? By performing 2's complementation. And this will be 0 1 0 0 1. Then 1, it will be 0 1 0 1 0. And sign will be negative because of negative overflow. Then you will get the result as minus 10. Okay. See, now see, observe this expression. At this time we were having x as 1, y as 1 and z as 0. So this represents the case of negative overflow. So what we can represent, the overflow condition will be represented by this particular expression. Guys, this expression has been asked so many times directly in GATE examination. So study this concept very carefully. Let us discuss a previous year question on the conditional flags. A processor that has carry overflow sign flag bits as a part of its program status word perform addition of following 2's complement numbers. We are already provided with 2's complemented numbers. It is asking the status of these flags after performing the operation. Let us perform the operation, and the operation is addition operation. See, numbers are 0, 1, 00, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 1. Perform addition. 1, 1 will give you 0, 1, 1, 0, 1 bit, 1, 1, 1, 1, 0, and this time 1 carry is given inside, 1, 1 again, 0, and 1 carry out of your MSB. So your carry flag is set to 1 because you are getting 1 extra bit out of your MSB. This was the condition for carry flag. Now check for overflow flag. Here you are getting carry into MSB and carry out of MSB as well. So here overflow flag is 0 and sign flag will also be 0 because MSB bit is 0. So tell me what is the output here? Output is option B. This question was asked in GATE CS 2008 and it was asked for 1 marks, and you can clearly see this is very easy to score this 1 mark. You should not lose marks in such type of question. This is the idea and this is how you can score a good rank in your GATE examination. So guys, that's all in this particular video lecture. We have discussed about program status word. In our next video lecture, we are going to study micro instructions and control units. Till that time, stay tuned and keep updated. And if you have some doubt, you can post. I can assure you that you will get reply for each and every doubt of yours. Thank you guys. Thank you again.